MDPs, multi-step MDPs, not just these one-step things. And to do that, we actually just need to do one trick, which is to replace this instantaneous reward that we had. So we were multiplying the score by the immediate reward. And to do a multi-step MDP, all we need to do is actually replace this immediate reward with the value function, the long-term reward. And that actually turns out to be the true gradient of the policy. And the policy gradient theorem tells us precisely what that means. That's just to formalize that, which is to say that if you start with some policy, then for any of those objective functions we considered earlier, the start state, the average reward, the average value, the policy gradient is basically given by this thing here, which is some expectation over the score function multiplied by the action value function, Q. So it basically tells you, again, how to adjust the policy so to get more or less of that particular action multiplied by how good that particular action was, or that particular action is in expectation. So you want to adjust the policy in the direction that does more of the good things and less of the bad things. And if you were just doing supervised learning and maximum likelihood learning, you'd have something which looked very, very similar, but you just wouldn't have this value function term here. You would just be adjusting things in the direction that made your policy achieve more of the things that your teacher tells you. And so what we have in reinforcement learning is instead of that, we adjust it for all actions. We just have to try those actions and see, well, are they good or bad according to our value function. Okay, so that's the policy gradient theorem. Let's consider the simplest way to actually use that now to make an algorithm. And we call this the Monte Carlo policy gradient, which is roughly the same as a really old, well-known algorithm called reinforce. And the idea is to update the parameters by stochastic gradient ascent. So we're going to get rid of that expectation now and just do something very practical. And we're going to use the policy gradient theorem. And what we're going to do is just sample that expectation. And the way we're going to sample that expectation is just to say what we wanted to, the term which appeared in the policy gradient theorem was this Q. So let's just sample Q. Let's just estimate Q by using the return as an unbiased sample of this Q. So we're going to be in a state, we're going to start by taking this action, and we're going to see what return we got, and we're going to use that as an estimate of Q. And we're just going to plug that in into our policy gradient to give us a direction, an estimate of the direction to move. And so every single episode now, what we're going to do is we're going to say, at each step, we're going to adjust our parameters a little bit in the direction of this score multiplied by the return that we actually got from that point onwards. And so what would that look like in an algorithm? Well, you'd start off, you pick some arbitrary parameters, you run your episode, and for that episode, so first of all, you run forward, you generate all of your rewards. This is like a forward view algorithm, so you have to go all the way to the end of the episode, generate your rewards. At the end of that, you know what the return was from each of your steps now. So now you go over each of your steps again, and you say, for each of those steps, we want to adjust our parameters a little bit in the direction of this gradient, the stochastic gradient, which is the score, how to adjust our parameters in the direction that gets us more or less of something, multiplied by this sample return from that step. So that it's as simple as that. It's a very simple algorithm. So this is the most straightforward approach to policy gradient. You just sample returns and you adjust your policy in the direction that gets you more of those returns.
And GT in this case is R?
GT? GT is the sum of the rewards. It's the return. So it's the sum of the rewards from the beginning of the from time step T onwards until the end of the episode. So it's the same definition of return that we've used before. So GT is the return, accumulated rewards from that time step onwards. Okay, so here's a little example. This is using that same Monte Carlo policy gradient with a particular policy parameterization. And the idea is that you start off with this puck in this world, and this puck is sliding along. There's very low friction in this domain, and you just get to exert a small force on it every time step, which can just slightly perturb its direction. And so if you're not careful, it can really overshoot its target. And then the target is given by this pentagon, which moves around every now and then, and it has to try and reach that target. And so if it gets a reward when it gets close to the target, and it's reset every 30 seconds, and then you just go. You just run trajectories, and you use this Monte Carlo policy gradient, and you update in the direction of those returns. So you measure your return, you go back over it, and you adjust your policy a little bit in the direction that gets you more of those returns, and then you see how this works. And so there's two things I want you to take away from this. The first is that you get this very nice, smooth learning curve. Value-based reinforcement learning tends to be much more jaggy. You end up with sometimes collapses and sometimes chatters, but you can do very well. The second thing to take away, so it solves this problem very nicely, but the second thing to take away is that the scale here, that, I mean, we're talking, 100 million iterations here to solve this problem. So it's slow. Monte Carlo policy gradient methods tend to be slow. They're very high variance. They're looking at this complete return of what happened, estimating the gradient from that return and moving in the direction of that estimated gradient. And so the rest of this class is going to be about using similar ideas but making them more efficient. Right? How to take this very nice idea where you get this smooth learning where you adjust the parameters of your policy to solve a problem, but make it more efficient, reduce the variance, make it work better. Okay, and so that's going to bring us to the final family of algorithms, actor-critic methods. So just a quick recap. So the main idea is that we've got this high variance estimators of the gradient now. So we had this policy gradient. We plugged in the return to estimate the gradient by taking a sample of our Q values. But that thing's very high variance. Like, it might be that I'm playing, Atari again, and on one particular episode I might get a score of 1,000, and on the next episode I might get a score of 0, and that's just in the randomness of what happens, because, over the course of 10,000 steps there are many, many different random events which might occur. This thing's very noisy. And the main idea of actor-critic methods is that instead of using the return to estimate the action value function, we're going to explicitly estimate the action value function using a critic, using a value function approximator. We're going to bring back the ideas from the last lecture, combine value function approximation with our policy methods. So again, we're going to have our true action value function, and we're going to estimate this thing using a function approximator, and then we're going to plug this in to our policy gradient as a substitute for Q pi. So what this means is that we now have two sets of parameters, and that's why these are called actor-critic methods. We've got a critic and an actor. And so intuitively, the actor is the thing which is doing things in the world. It contains the policy, it's picking actions, it's actually making the decisions of what to do in the world. That's why it's called the actor. Whereas the critic doesn't actually take any decisions, it's just watching what the actor does and seeing whether that's good or bad, evaluating that thing, saying, oh, those decisions were good, they got a score of 1,000, or they got a score of minus 1,000. So we're going to combine those two things together, the actor and the critic, and the main idea is now to use an approximate policy gradient. Instead of the true policy gradient, we're going to adjust the actor, we're going to adjust the policy in the direction which, according to the critic, will get more reward. So the critic's going to say, hey, I think that if you go in this direction, you can actually do better. And then the actor's going to move in the direction of that gradient. And so the way we're going to do that, we're going to take our original policy gradient algorithm, which was an expectation of the score multiplied by the value function. That was our policy gradient theorem. But we've replaced the true action value function with this estimated approximate value function, where we've got our neural network or whatever to estimate this thing. And what we're going to do then is, at each step, we're just going to move a little bit, using stochastic gradient ascent. Every step we're going to move a little bit in the direction of the score multiplied by a sample from our own function approximator. So the critic is saying, hey, I think this thing is good, or I think this thing is bad, and then we move a little bit in the direction that gets more or less of the things that the critic says are good or bad. Okay? So how do we estimate the action value function? How do we estimate Q? What do we do for the critic? Well, that should be familiar. That's what we did last lecture. We started off with this problem of policy evaluation. We want to know, if I'm following some policy pi, if I'm following this policy pi, we're trying to estimate this Q pi. We're trying to say, how good is that policy? We're not trying to optimize it. We're not trying to build a critic that estimates Q star. We're just trying to say, according to this current behavior, how how good is it? How much reward will I get under this current behavior? And then we're going to use that to point us in the direction that will improve our policy. So a way to understand this is we want to say, how good is this current policy pi u for our current parameters u? We want to know how good is that thing. And so we can use everything we've learned so far, Monte Carlo policy evaluation, temporal difference learning, TD lambda, pick your favorite policy evaluation algorithm, least squares, temporal difference learning, anything you like, throw it into the pot, get an estimate of your action value function, and use that to adjust your actor. So, here's a canonical example, just to make things concrete. So let's say we were using a linear value function approximator for our critic. So we're going to estimate Q by using some features of our state and action multiplied by some critic weights, V. So in this class, we're going to use V for the critic parameters, U for the actor parameters, just to keep those separate and distinct from what we did in the last lecture. So we're going to estimate our critic just by using a linear combination of features. And then the critic we could just update in the usual way using linear TD0. And the actor, we can update the actor parameters U by policy gradient, score multiplied by what the critic says. So that would look something like this. This is the Q actor critic. So basically what this is saying is that every step of the algorithm, now we don't need to wait until the end of the episode. This is now an online algorithm which we can, every single step, perform an update because we're using TD in our critic. We don't need to wait till the end like we do with Monte Carlo. So every step of our episode, or every step that the agent experiences, we're going to sample the transition, we're going to see what the reward was, we're going to see where we ended up after that step. We're going to pick an action according to our own policy. We're going to get the TD error between the value before that step and value after that step, just like we did in the previous lectures. Now we're going to update our critic in proportion. Our critic we can update a little bit in the direction of the TD error multiplied by the features. So that was linear TD0, so that's from last lecture. That's how to update our critic in a direction that minimizes the error between what we thought was happening before, what we thought the value was, and what the value ended up being after one step. This is like correcting our errors and making ourselves self-consistent. And we're also going to adjust the actor. We're going to adjust the actor in the direction that gets us more of the things that the critic says are good. So that's the actor-critic idea, using a canonical case using linear TD. Okay, any questions so far? I'll just pause there before we're going to start adding more tricks to reduce variance, make these algorithms more efficient. So if you're feeling uncomfortable, now is the time to say, because we're just going to layer more pieces on from here on in. Yes, good.
Sorry. So you have a policy, you get a estimate, and then from that estimate you try to get another policy out. Is that true?
That's right, yeah. So we can think of this as another form of generalized policy iteration, where we start off with a policy, we evaluate that policy using the critic, and then instead of doing greedy policy improvement, we're moving a gradient step in some direction to get a better policy. So it's just like our familiar machinery, where we're making the policy better and better, and every step we're evaluating that policy, moving a little bit up the gradient to find a better policy.
My question is, choosing the first policy, does it differ?
Choosing the first policy, you can pick an arbitrary policy, so you initialize your policy parameters however you want. It could be, typically now we've just got parameters though, we're not using greedy anymore, we've just got some parameters, and those parameters determine our policy. I'm scaring people away from it. Okay, and we're making those policies, we're following the gradient so as to make those policy parameters better, so that our policy gets more and more reward out of the MDP. Okay, so we start off with some policy parameters, that determines our behavior. We want to make that behavior better and better and better. There's no greedy anymore, no epsilon greedy. The policy itself determines how we move around in this environment. These policy parameters, we're always picking actions according to the policy that's determined by these parameters U. So, yeah, one more question.
But if your policy was epsilon greedy over your Q function,
Mhm.
do you like fall back to Q then? What happens?
Let me go back to a slide that I kind of skipped at the beginning because the projector was down. This one. Okay. We had this in the introduction, but I think it's worth reiterating. So let's classify our algorithms into either whether we have a value function that we represent, whether we have a policy that we represent, or whether we have both. That's what this Venn diagram represents. If we have a value function, if we represent that value function, we call it value-based. If we have a policy that we represent, we call it policy-based. And if we have both of these things in our algorithm, we'll call it an actor-critic. Okay? And